In this video, we continue in chapter 7, covering section 7.3, where we are going to take a look at symmetric matrices and orthogonal diagonalization. So we're going to build on the diagonalization skills from section 7.2 and see some more ways to diagonalize for orthogonality. So our learning objectives are to recognize and apply properties of symmetric matrices, recognize and apply properties of orthogonal matrices, and then to find an orthogonal matrix P that orthogonally diagonalizes a symmetric matrix P, matrix A. And so we'll talk about in the second video what that means to orthogonally diagonalize a matrix. So let's start by talking about the properties of symmetric matrices. So remember, a square matrix A is symmetric when A equals A transpose. We saw that back as early as chapters 2 and 3. And so theorem 7.7 gives us equivalent properties of symmetric matrices. So if A is a symmetric square n by n matrix, then A is diagonalizable. All the eigenvalues of A are real. And if lambda is an eigenvalue of A with multiplicity k, then lambda has k linearly independent eigenvectors. And this matches what we saw in our previous examples, because we saw examples where the eigenvalues had multiplicity 2 and they had 2 linearly independent eigenvectors. So essentially what this is saying is that the eigenspace of lambda has dimension k. So this theorem 7.7 is called the real spectral theorem. And the set of eigenvalues of A is called the spectrum of A. So because this involves a conclusion that all the eigenvalues are real, we do need some complex analysis having to do with complex numbers to prove that. And so the proof of theorem 7.7 is actually in chapter 8.5 as part of theorem 8.10 in our textbook. So we won't prove this until we get to studying complex numbers, but you can look ahead to section 8.5, theorem 8.10 if you'd like to see it. So let's prove that every 2 by 2 symmetric matrix is diagonalizable. So here's a symmetric matrix, A, C, C, B. We've got C's in the diagonal here. So we want to show this is diagonalizable. And because this is generic in terms of A, C, and B, then this is going to be true for all 2 by 2 symmetric matrices. So let's take a look at the characteristic polynomial. So the determinant of lambda I minus A gives us this, lambda minus A and lambda minus B on the diagonals, and negative C on the opposite diagonals. So when we expand that out, we get lambda squared minus A plus B as the coefficient on lambda, plus AB minus C squared. And then this is a quadratic in terms of lambda. So the discriminant of this polynomial is going to be A plus B squared minus 4 multiplied by AB minus C squared. Remember, the discriminant is B squared minus 4 AC. So that's the extra A in here. Is there an extra A in here? We might be off by an A. So the discriminant is B squared. I thought it was minus 4AC, but maybe the A got tied up in here. Maybe it's a typo. We'll see as we expand it out. So this works out to be A squared plus 2AB plus B squared. And then here's a minus 4AB, and then the two negatives give us plus 4C. Then we get to combine the 2AB and the minus 4AB. So that's A squared minus 2AB plus B squared plus 4C. So that factors to give us A minus B all squared plus 4C. All right, and I realized when I said 4AC here, I'm mixing my A's. So in terms of coefficients, the A here is a 1 because we've got just a lambda squared. So when I said 4AC, I was mixing up the A in terms of the lambda squared's coefficient as 1 with the A that is here in the equation. So they're different A's. So everything works out because it's 4 times 1 times AB minus C squared. So we're okay there. So everything factors as we think it should. So now we're here at our discriminant, and the discriminant here is the sum of 2 squares. So it's got to either be a 0 or positive. We can't get a negative here with a sum of squares. So if is 0 if we have this, A minus B all squared plus 4C squared is 0. Then that's going to say, well, A is B and C is 0. So that's already a diagonal matrix because we've got C is 0. The other possibility is that A minus B squared plus 4C squared is positive. So then by the quadratic formula, the characteristic polynomial of A has two distinct real roots, which means that A has two distinct real eigenvalues. So A is also going to be diagonalizable in that case as well. All right, let's take a look at an example here. We want to find the eigenvalues and eigenvectors of this matrix here. And then we want to know are the eigenvalues real and what are the dimensions of the eigenspaces. And we're going to find the angles between the eigenvectors. All right, I have included on here from my old lecture notes when we used to use a TI calculator, the TI screenshots. I'm also in the next slide going to show you the Sympy screenshots. So if you want to do this on your calculator, it's just fine. You just go into the matrix tools and define the matrix as X, and then the rest of the commands are typed out here. So we are solving 0 equals the determinant of lambda I minus A. And so here's how they typed it in the calculator. They called matrix AX here, and then they said factor, and then in parentheses determinant, and then they called lambda T. So T minus the 3 by 3 identity matrix, or sorry, T times the 3 by 3 identity matrix minus matrix A that they called X here, and we got the factorization. We can do the same thing in Sympy. So in Sympy, the identity matrix has a cute little name. It's I. Is the name of the function there, and then you just put your dimension n in parentheses. So if you type I3, you get the 3 by 3 identity matrix here. So we are going to do our factorization. So I entered matrix A here, and then I told Sympy factor, and then in parentheses determinant T times I of 3, that's a 3 by 3 identity matrix, minus A, and I closed it off with double parentheses, and I got that same factorization as you would get on the TI calculator, T minus 2 times T plus 1 squared. And note if you're using live.sympy.org, T is predefined as a symbol in there. So you can't just use any old letter. You have to use, I think, X, Y, or T, maybe Z also, are predefined as symbols. Otherwise, you have to define your value as a symbol. And if you're running Sympy on another programming setup, you will have to define T or whatever value you're using as a symbol so that this will work. But you see our Sympy calculations match our TI calculator factorization calculations. So you are welcome to use either to factor. Okay, so our eigenvalues, -1 has multiplicity 2. So we've got lambda 1 equals 2, and then lambda 2 and lambda 3 equal -1 from solving this factorization equal to 0. So all the eigenvalues are real. And so now we want to solve lambda 1 I minus A multiplied by a vector x1 equals 0 using reduced row echelon form. So we're going to write x1 as xc. This is the Greek letter xc that I've got here in the notes. You don't have to use xc. You can still call it x1, x2, x3. Just make sure you don't mix it up. So when we do our reduced row echelon form, we get zeros in the last row. And you can do this in calculation in Sympy and C, you get a match. So that means our x3, our c3 here is a free variable, so we're going to call that t. And then when we solve here, we also get x1 or c1 equals t, and x2, they should say 2 or c2 equals t. So you can see that right here because 1, 0, -1, when you solve that, you're going to get 1 equals t. 1 x1 equals t, or 1 c1 equals t, and the same for x2 or c2 equals t. We're just using c here because we're going to have another vector for the other eigenvalues. So the solution here is t, or t multiplied by 1, 1, 1. So we can say our eigenvector for x1 is 1, 1, 1. And the eigenspace of lambda equals 2 is one dimensional because it has multiplicity 1. Here's how you do this in Sympy. You do 2 times I3, that's the identity matrix, for 3 by 3 minus A. Then you do dot reduced row echelon form. Remember, we leave the parentheses blank. And if we just want the matrix, we do in brackets 0, and that calls out the first value. So that's just the same value the TI calculator had. And then you'd say like C1 minus T equals 0. And then that's how you get the C1 equals T. And then the same thing for C2, or if you wanted to call it X1 and X2, that's fine as well. All right, so now we're gonna solve lambda 2I minus A multiplied by X2 equals 0, and lambda 3I minus A multiplied by X3 equals 0 using reducer echelon form. Lambda 2 equals lambda 3, so you can see down here is how we type it in Sympy, and our resulting matrix just gives us ones in the first row. Same thing if you want to use the TI calculator. So we get two free variables here. We get S and T, we'll call them, you can use whatever letters you want. And again, here we're doing the C1 and C2, but you are welcome to not call it C1 and C2. If you just want to call it X1 and X2, that's fine. We did that here in the notes so you didn't get mixed up between all the X's, because we're calling the vectors X1 and X2, but you could call it some other letter if you like. All right, so then we get here solving our, 1, 1, 1 and zeros everywhere else in the top row, that the first value C1 is going to be negative C2 minus C3. And so we say that's just negative S minus negative T, and then we've got S and T. So for free variable S, if we factor that out, that's negative 1, 1, 0 factor. And for free variable T, if we factor that out, that's negative 1, 0, 1. So our other eigenvectors X2 and X3 are the negative 1, 1, 0 and negative 1, 0, 1. And down here, I did the calculation in the Sympy that matches with the graphing calculator here, negative 1 identity matrix 3 by 3 minus A in reducer echelon form. Over here in Sympy, I checked the eigenvectors so you can see negative 1 here has multiplicity 2. And these are our same eigenvectors and their match here. And then here's our eigenvector for 2 that has multiplicity 1. And our eigenvector there is 1, 1, 1. So we got an exact match here with the free variables. Just remember with the free variables, sometimes you get different scalar multiples when you do your eigenvectors in Sympy than if you do it by hand. And that's because with free variables, there's infinite possibilities. So now the last part of our calculation here is to find the angles between the eigenvectors. So the eigenspace of lambda equals negative 1, which has multiplicity 2, that's two-dimensional. We said that already, but I pasted it in here as well. So here, let's do the dot product. So x1 dot x2, I just wrote this horizontally to dot them out. We get a 0, so x1 is orthogonal to x2. Then x1 dot x3 also gives us 0. So x1 is orthogonal to x3. And then we have to dot out x2 dot x3. So following our dot product formula, making sure we norm them on the bottom here, we end up with 1 over root 2 times another root 2, or 1/2. So the angle between x2 and x3 is the arc cos of 1/2, which if you consult your unit circle, that's just pi over 3. Okay, in the next video, we're going to talk about what it means to diagonalize an orthogonal matrix.